Good evening, everybody. I'm very proud to present to you the second presentation for tonight. My name is Nadine, and I'm the coach for Team T Systems. Before we begin, I would like to take a moment to thank our customers, Dr. Stefan Fecklas for giving us this amazing opportunity, David Kabat for joining us here tonight, also our awesome project lead, Konstantin, and our 6 amazing developers. Now I will head to Miriam and Marco, who will take you along this presentation, and enjoy.
Thanks, Narin. So, let's get started. Every year, an average of 370 natural disasters happen all around the world. For instance, earthquakes, tornadoes, hurricanes, and more. In this scenario, first responders are deployed in order to help and save people. For a first responder, the lack of fast and accurate data may lead to an improper diagnosis, which may cause long-term health conditions for a patient or even death. In the case of an industrial facility, a data center, for instance, outages and failures happen often than expected. In this scenario, a power outage costs slightly more than 7,900 million euros per minute. So, for a technician in this situation, it is critical to quickly identify the root cause of a problem, having the right information at the moment he needs it. So, how can we support these professionals using technology? Well, we are developing a tricorder application capable of identifying smart objects, retrieving real-time sensor data, and providing a context-aware user interface. But now, let us show you a video explaining one of the visionary scenarios that we prepared. In this scenario, a team of professionals is deployed in one of the facilities of the systems with the purpose of restoring the communication in one of their data centers. So, enjoy the video.
Tricorder is capable now of scanning smart objects, whether it's a machine or a human. For humans, we are measuring the following vital parameters. We have an alarm!
Our data center in Berlin is under attack. Group Bravo, I want you to lead the rescue operation, save people and restore the connection to the object. Let's see what your tricorder can do.
Go ahead. I will use the tricorder to save his life.
So, let's quickly review the scenario that we just saw in the trailer. There is a data center with a machine. Suddenly, an earthquake happens, and the machine gets damaged. As a response, the technicians Max, Fedor, and Marco are deployed in order to repair the machine. On their way to the data center, another earthquake happens, and the technician Marco gets injured. So, as a response, Fedor, with the help of his tricorder, scans the vital parameters of Marco in order to provide a quick triage. Meanwhile, Max continues his way to the data center in order to repair the machine. Once in there, he identifies the machine and proceeds to use the capabilities of his tricorder in order to detect the problem and proceed to fix the machine. Once he knows what the problem is, he uses the augmented reality capabilities of his tricorder in order to fix this machine. When he's done, the machine is fixed and the problem is solved. Mission accomplished. So, what are the requirements for such a system? Well, we need to support humans, and for this, we need to build a system in a human-oriented way instead of a technology-oriented way. Apart from this, we need to integrate augmented reality visualization within the system. Another important point is we need to integrate the smart textiles within the design. Another important point is that the tricorder has to be scenario-independent, meaning it has to be able to distinguish between different kinds of smart objects. I'll cover this point later on. Last but not least, we need to integrate augmentation of dynamic and interactive objects such as notes and instructions within the design. So, let's quickly show you the components of the system. Here we are dealing with the smart objects. A smart object can be distinguished between a machine or a textile. Those are composed by sensors, actuators, and nodes. Every smart object is capable of storing data in a data storage. For the case of the machine, it is stored in a cloud service environment, whereas for the textile, it is a microcontroller within the textile itself. Last but not least, the smart objects are capable of storing incidents. Incidents are understood as a deviation in the regular parameters of the sensor values coming from the device. So now my colleague Miriam will show you the top-level design of the system.
So let me show you a quick overview of our whole system architecture. We have our smart objects, which are recognized by our tricorder. In an extreme environment, it is really important that the person who is using the tricorder can see all the sensor measurements from the smart objects. Therefore, data has to be sent to the tricorder from the smart objects. There's also a data flow from the tricorder to the smart textile. This is the data that controls the triage, which is a LED light that indicates the condition of the injured person. Now I want to present you our system design with our different subsystems. Our first subsystem is our smart machine, which consists of sensors. The data storage for the smart machine is our cloud servers. We also have another smart object, our smart textiles, which consists of sensors, an actuator, our triage, and a microhub, which is the data storage for our smart textile and is directly integrated in them. Our last subsystem is our tricorder, which consists of a textile data manager, which handles the data it gets from the smart textile and sends it to the UI. Our smart machine data manager does the same for the data it gets from the smart machine. Now I want to show you our data flow in our system. We have sensor measurements from the smart machine, like magnetic sensor data and voltage sensor data, which are sent to our cloud services. From there, the data is sent to the smart machine data manager in the tricorder, and there it is handled and sent to the UI. Sensor measurements from the smart textile, like humidity sensor data and temperature sensor data, is sent to the microhub in the smart textile, and from there, the data is sent to the textile data manager, which is also in the tricorder. As I explained before, there is one less data flow in our system. It's the data for our triage. The data flow goes from the textile data manager in the tricorder to the microhub in the smart textile, and from there, the data is sent to our actuator, and the triage can shine in a different light. I now want to show you a quick live demo of what we have implemented so far. Well, maybe you have all been wondering why Marco is lying down on the floor there during our design review. Because he is wearing smart textiles, we can change his vital parameters and can see if something is wrong with him. As you can see, there are patches on the smart textile which visualize our sensors, and we need them to later show our measured sensor value in our app. So we can use our tricorder now to scan his vital parameters. We first have to initialize our tricorder and have to scan the environment so the tricorder has enough orientation in the room. Then we can focus on one of the patches and can look if this vital parameter is okay. As you can see, the tricorder has detected a patch and now connects to the smart jacket and retrieves the sensor data. We can see this is a heart rate monitor and the heart rate is okay. Okay, we don't have the sensors now. Well, but maybe Marco needs something to drink, so we can check his humidity. So we can focus on another patch. The patch is detected, and we are retrieving the sensor data. And you can see the humidity is maybe too low, so maybe he should drink a beer afterwards. Now I want to show you a visualization of the algorithm of the patch recognition. We first use a vision rectangle detection to detect if something in our camera view could be one of our patches. We then take this captured image from the AR frame and we are cropping the rectangle out of it. We then use image recognition with an Inception V3 model, which we retrained with Keras and which could be used by a CORE-ML framework. This model then decides if the recognized rectangle is one of our patches or not. If it's one of our patches, we display the measured sensor value using AR on our patch in our app. This is part of our smart object recognition, which is one of our main features. We have implemented the smart object recognition so far for the smart machine and for the smart textiles, and we are working on some few other main features we will hopefully show you in the client acceptance test. If you have any questions, feel free to ask, and thank you for your attention.
Good afternoon, everyone. David Kabat from T-Systems. At first, thank you very much to the whole team for all the work they've performed, and also for a very nice presentation. Yeah, and well, my question would be, what was the biggest problem? What you had to deal with in a project, or was it everything smooth running machine from the beginning to the end?
I can talk from our side for the smart textiles, but I think the smart machine part had the same problems. We had, at first we had a few problems recognizing our patches and recognizing the machine because we had to learn a little bit of machine learning and deep learning, and we had problems to find frameworks which could, and where we could create models and retrain our models. And then we had the problem that we couldn't localize our patch. And for that, we are now using, at first, the vision rectangle detection. So we have the X and Y coordinate. And for the Z coordinate, we now use feature points, and we execute multiple hit tests on these feature points, because if we only do one hit test, we have something like a fuzzy result. And so we do a lot of them, and then we are calculating a center, and then there we can put our visualization. As you have seen before, there are visualization on the patches. We made that with this calculation.
Thank you very much. So good luck with the next phase of the project.
Thank you.